This video will give insights on applications of signal processing and show some use cases of different domains with Altair Compose. First of all, signal processing is an engineering field whose goal is to read, treat, synthesize, and analyze signals. And a signal is a data set that has information about any quantity that can be measured. And that's why this engineering field has so many applications, like control systems, durability, NVH, electronics, and many others. And today we're going to talk a bit about applications in these domains here. So first of all, speaking a bit about control systems, there is an intimate relationship between control systems and signal processing because they deeply rely on Laplace transform in continuous time signals and Z transform in discrete time signals. And the formal definition of Laplace transform means that it transforms a function of a real variable t, which is often time, to a function of a complex variable s, which is complex frequency. And usually, control systems are more interested in time domain behavior, whereas digital signal processing is more interested in frequency domain. But both are part of the same mathematical formulation, like I just explained. And the bottom line is that signal processing has a set of tools that can be used for control systems, such as filters. The following example will show how to use Kalman filter in state space matrices. So, Kalman filter is an algorithm that estimates the state of a system based on measured data, which can be used to estimate the output based on measurements that contain noise. So first of all, let's construct the state space model using SS function. A is the state matrix, B is the input matrix, C is the output matrix, and D is the direct transmission matrix, using the conventional notation for state space models. Some other arguments may be given to SS function, such as the sampling time, and the default is to consider the model as a continuous time model if no input is given. Now we are ready to use Kalman filter given the system as the first argument. The other arguments are related to the covariance of wide process noise, the covariance of wide measurement noise, and the cross covariance matrix between these two noises. And these covariances are a measure of uncertainty in the system. The outputs of the function, the state space linear time invariant form, the gain matrix that minimizes the covariance of the state estimation error, the steady state covariance of the estimation error, the steady state innovation gain matrix, and the steady state error covariance of the error between the actual states and the updated state estimates. And now, speaking a bit about durability. Durability tests are strongly data-driven to evaluate fatigue aspects like damage and life of components, and they primarily rely on the following steps. First of all, formulate the problem. Second, set the instrumentation and data acquisition. Third, prepare the signal. Fourth, process the signal. And fifth, interpret the results. And all these steps actively depend on signal processing to generate an accurate assessment of the component life. Regarding the formulation of the problem, the durability specifications directly affect how the data should be acquired and therefore how the signal will be processed afterwards. And it's the same situation with the test specs. Secondly, the instrumentation will determine parameters like sampling frequency and strain gauge parameters to reduce the noise and disturbances in the acquisition process. Third, preparing the signal means that drifts and spikes should be removed in time domain analysis, whereas filters in the frequency domain may also be applied. The fourth step is that signal processing will navigate from time domain to frequency domain, compute power spectral density, and generate a time history based on a PSD, for instance. And finally, interpreting the results help to calculate the damage and the maximum displacement that our component is exposed to. The following example is how to create a time series based on a PSD. So, based on PSD test specifications, it's possible to generate a time series whose characteristics and frequency domain are equivalent to the input PSD. First of all, let's plot the input from the test spec in log scale in both axes to have a look at the PSD. Secondly, give the sampling frequency and the number of samples that the output time series must have. Also, let's separate the PSD and the frequency vector from the input signal. Then, calculate the frequency resolution based on the sampling frequency and the number of samples, and create a new frequency vector based on it. The next step is to interpolate the PSD values for the new frequency vector. We must also take into account the root mean square level of the PSD. And as PSD is defined as the amplitude squared, therefore the square root of the PSD is the amplitude. And the test spec PSD was single-sided, and that's why we need to compute the amplitude for a double-sided signal. Then let's create a white noise, which is a random signal having equal intensity at different frequencies. And finally, compute time series with inverse fast Fourier transform, scaling it to the same RMS level of the PSD. And we may now plot the time series whose frequency domain information matches the input PSD. When we click on the first figure in the project browser, we see the input PSD. On the other hand, the second figure that we just saw has the time series based on the PSD. Let's talk about NVH and signal processing now. So NVH has become an automotive branch with increasingly demand for reduction of vehicle noise to improve the driver's experience as a result of stronger competition of players in this market. And moreover, spectral analysis is relevant to investigate the nature and characteristics of acoustic sources, because the NVH measurement procedure does not only depend on the sound pressure level, but also on the spectral composition of the sound. And the assessment of how critical a noise is takes into account the distributions of critical bands in the human hearing. Also, it's useful to perform the decomposition of experimental data to separate environmental background sound, noise, and other sources of acoustic response. The following example is how to synthesize an audio based on a signal. So, synthesizing audio files based on experimental data gives a better understanding of the user experience when driving the vehicle. So let's create a random signal considering 44,100 Hz as the sampling frequency, because this is a common value for this purpose. Then, normalize the signal to bring the amplitude to a target level. Now we are ready to couple audio capabilities of SciPy package with OML. OML has a bidirectional bridge with Python that allows the integration of both languages in the same script. This is accomplished with functions to export variables from OML to Python, to evaluate Python files, and to get variables back from Python to OML. Using this bridge, export the signal to Python, evaluate the Python file that will create the audio file, and get back to OML the variable that displays the status of the script. In this case, it was successful, and we see that an audio file was generated. Now, covering a bit about electronics, there is a wide range of powerful applications using digital signal processing, such as wireless communication, where signal processing routines read the analog signal, convert it to digital, encode it, and approximate the data packet before transmitting it. Data compression, to reduce the size of data packets in order to optimize the storage capacity and the use of network bandwidth. Autonomous driving, where signal processing based systems are used to detect vehicles as they approach and to accurately locate them using GPS to compute the distance between the receiver and multiple geostationary satellites. Audio processing, used in subfields like speech recognition, noise cancellation, music identification, and transmission in general. Let's see an example how to compress an image using singular value decomposition. So data compression is key for the transmission of data with smaller data packets, and regarding images, they are represented by a rectangular array where each element corresponds to the grayscale value for that pixel. And when we consider colored images, there is a third dimension with size equals to 3, which stores the intensity of red, green, and blue colors for each pixel. Among many other applications in linear algebra, singular value decomposition has become a new paradigm for image processing because it's a matrix decomposition method to reduce a matrix to its constituent parts, where U and V are orthogonal matrices, and S is a matrix with descending positive values on its diagonal and zeros everywhere else. So when compressing the image, the matrix multiplication is not performed to the very last terms of S and V because the values considered to be small enough are dropped. And the new matrix with the information that will become the compressed image is based on the truncation of those terms after the first k terms. And in order to measure the performance of the SVD image compression, we can compute the compression factor based on this ratio, where M is the length of U matrix and N is the length of V matrix. And using K equals to 120, we get a compression ratio of approximately 3.15. And we can see some flaws in the generated image. As we increase the value of K, we compress less the image and we achieve a better image quality. Please visit Altair Forum, a place where users can interact, ask questions, exchange information, and post about model-based development.